Hello students, in lecture 14 of your course Elements of Discrete Mathematics, here we study the complement of a subgraph, what is meaning of it and how we determine, how we find it, complement of a simple graph, certain example and simple exercises related to these concepts, and what is the meaning of a regular graph, what are the bipartite graphs and complete bipartite graphs. So first, we discuss the complement of a subgraph. So before giving the definition of the complement of a subgraph, here with this example, I demonstrate you what is the meaning of it. You visualize it and then you can easily write the definition. You can see this is a graph G whose vertex set is V and the edge set is E. Obviously here V1, V2, V3, V4, V5 and V6. This graph has 6 vertices and 1, 2, 3, 4, 5, 6, 7, 8 and 9 edges. Now from this graph G, if we delete certain edges and we are deleting certain edges here, for example edge 8 is deleted here, then 9 is deleted here, and yeah, this is 1 is deleted here and h2 is also deleted over here. So in this way we obtain this graph H. Then obviously this graph H has the vertex set V dash and the edge set E dash, and this graph is a part of this original graph G. So this H is said to be the subgraph of G. Now we want to find the complement. We want to find the complement of this subgraph H. How to find it? In fact, all the edges which are there in this subgraph H should be deleted from the original graph, and whatever we are left with this situation, this type of subgraph you can see. So in fact, when we are deleting 7 from this, so obviously 7 is deleted over here, and the edges which are there, all the edges should be deleted from this graph, and we are left with this situation, and finally we obtain the subgraph H dash. Then this subgraph H dash is said to be the complement of this graph H. And one thing you can observe over here, the vertex set remains the same, that all the vertices will be present over here, and edges are different because it will consist those edges of G which are not in H. Therefore this is the complement of graph H. Now definition of this can be given in this way. Let H equal to V dash E dash be the subgraph of the graph G, and the complement of subgraph H will with respect to graph G is a subgraph H dash, which can be represented like this. Then we come to complement of a simple graph. You know, a simple graph do not have self loops and the parallel edges. Let G equal to VE be the simple graph. The complement of G is a graph G bar equal to V E dash such that an edge E belongs to E dash if and only if E does not belongs to E. That means complement will consist all those edges which were not present in G. For example, here this is the case of a simple graph with 5 vertices, and the edges are there. Now you can see if a very simple formula, if you have n edges and you want to form a complete graph, then number of edges in a complete graph is nc2, that is n into n minus 1 by 2. So here this is the simple graph with 5 vertices, so it must have 5c2. A simple graph at the most maximum it can have 5c2, that means 5 into 4 divided by 2, that means this is 10. It must have a complete, if this simple graph is complete, then it must have 10 edges. But now here you can see the number of edges are 1 2 3 4 5 and 6. That means 4 edges are missing. So when you want to find the complement of this graph G, the edges which are missing over here should be incorporated here, because here you can see here there is no edge between V2 and V3, so you will write and you will put an edge between V2 and V3. Again, you can see there is no edge between V1 and V4, so I'm writing here, I'm putting the edge between V1 and V4. Similarly, there is no edge between V3 and V5, so this is for V3 and V5. Again, there is no edge between V2 to V5, so the one edge is there, V2 to V5. So in this way, you can say the edge E is here. If I say that this is edge E, this E is present in fact, E dash, but this E is not present in E, the edge set of this graph G. So this is the concept here. This is the complement of a simple graph. You can understand from this example. Now the self complement. A simple graph which is isomorphic to its complement is called self complementary graph. For example, again we are having this graph with 5 vertices, and if I find the complement of this, then definitely I shall have the edges which are missing here, because again it is a graph of 5 vertices, so it must also have 10 edges. It must have 10 edges. So 5 edges are there. What are the remaining edges? You can see over here. These are the edges which are not present over here. So this is complement of this. Now here you can observe that this graph G and G bar both will be isomorphic. And how you check the isomorphism of graph, we have already discussed in the earlier lecture. Now let's do one example here, very simple one. What is the maximum number of vertices in a graph with 35 edges? With 35 edges are given, and all the vertices are of degree at least 3. That means in the graph, the vertex of the degree of each vertex is either 3, and it may be more than 3. The vertex degree of vertex may be more than 3. So this is the situation. Here you are not given the number of vertices, you are given the number of edges, because graph consists of 35 edges. Number of vertices are not given. You have to find the approximate number of the vertices. So you suppose that the number of vertices is equal to n. The number of edges in the graph is already given is 35. The contribution of each edge to the degree. You know, if this is the edge, then here must also be a vertex, suppose v1, and this is v2. Now the contribution to the degree due to each edge is 2, because it is contributing 1 degree to this vertex and 1 degree to this vertex, right? So sum of the degrees of all the vertices. So in fact 35 edges are given, and each edge contributes the number 2 to each to the degree. So 35 multiplied 2, it is 70. So sum of the degrees of all vertices is in fact equal to 70, but you are given that degree of each vertex is greater than or equal to 3. So n is the total number of vertices. So you can say the sum of the degrees of all vertices is greater than or equal to 3n. But sum of the degrees is already given. We have calculated is 70. So 70 greater than or equal to 3. So this inequality can be satisfied with the number 23. If you write here n23, then it is 69, then 70 is greater than or equal to 69. So n equal to 23 is the appropriate number which satisfies this inequality, and hence here we can say the maximum number of the vertices in a graph with 35 edges and all of its degree of each vertex is at least 3 will have 23 vertices. Now the exercise is there. You can solve these 3 problems. Prove that G is self-complementary, then G has 4k or 4k plus 1 vertices, where k is an integer. The second problem, is it possible to have a group of 9 people such that each person is acquainted with exactly 5 of other people? That means if you have a group of, I just give you one hint, if you have group of 9 people, 1, 2, 3 and 4, 5, 6, 7, 8, 9, then is it possible that each one, suppose this is person 1, that is acquainted with 5 other people. That means it is acquainted. Acquainted means he know or he have some information about those 5, that this one and this is third and let this is fourth and this is 5. So in this way, is it possible? Similarly, if you must consider the second person, that it must also know other 5. So is it possible to have that kind of situation? If it is possible, then how it is possible? And if it is not, then you have to justify your answer. Draw the complement of the circuit graph C4. You know, the circuit graph C4 means it will consist of 4 edges. So this is the circuit graph. It will have 4 vertices and the 4 edges. Now you have to find the complement of this. You have to draw the complement of this circuit graph. Then come to the regular graphs. Regular graphs are those in which the degree of each vertex is same. And if we have a regular graph of n vertices, then it is called a n regular graph. A regular graph of 3 vertices is called the Patterson graph because it was first developed by the Patterson due to the utility problem, which you will see later. So here lots of figures or the graphs are given. All of these are the regular graphs, and the figure is taken from the Wolfram Math website. So here you can see this is one, only one vertex is there and there is no edge. So definitely here the one vertex is there and degree is 1. And here we have this graph, and which have 2 vertices and 1 edge. So now you can say this is vertex v1 and this is vertex v2, and degree of each vertex is 1. Its degree is 1, degree equal to 1, and similarly degree of this vertex is also 1. So you can say in this graph degree of each vertex is same. Now look at this one. Now here this is the graph with 3 vertices and 3 edges. So I say that the vertex v1 and let this is v2 and this is v3, and you can see that 2 edges are incident upon it, and therefore degree of this v1 is 1. Similarly, degree of this v3 is also not 1. This is basically 2 and this is 2, and again degree of v2 is also 2. So you can say in this graph also degree of each vertex is same, that is 2. So this is also a regular graph, and I can say this is 2 regular graph, and here this is also a 2 regular graph. Now we look at this, you can see the three edges are incident on each of the vertex. So this is a 3 regular graph, this is a 3 regular graph, and so on and so forth. You can check in all these, some are 3 regular graphs. For example, all these are the 3 regular graphs. Okay, then this is also a 3 regular graph. You can see that this is a 4 regular graph, and so on and so forth. You can check. Then the bipartite graph. Bipartite graph can be used to model many type of applications that involve matching the element of one set to the elements of the other. A simple graph G is called bipartite if its vertex at V can be partitioned into 2 disjoint sets V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex in V2. And note that no edge of G connects either 2 vertices in V1 or 2 vertices in V2. When this condition holds, the pair V1 V2 a bipartition of vertex V of G. In fact, what is the partition of a graph? What do you mean? Suppose we have a non-empty set V, then a partition P is the collection of 2 subsets of V basically. Here this V1 is subset of V as well as V2 is subset of V. And then partition in this P is said to be partition if 2 conditions are satisfied. Number 1, V1 union V2 is equal to the whole set V, and the second condition is that V1 intersection V2 is equal to 5. So in order to, a graph is said to be a bipartite graph if the vertex set can be partitioned in this way that 2 vertex sets are disjoint, and there must be a connection uh, between an edge or between a vertex of one set to the vertex of the another set. Let us see this. C6, that is circuit of length 6. This is C6, circuit of length 6, is a bipartite graph, because here we can partition this graph into two sets. This is V1, which consists V1, V3 and V5, and second V2, V4 and V6, and every edge of C6 connects a vertex V1 and a vertex of V2. We can restructure this graph in this way. You can see here, if we write these vertices, there is connection. Suppose I am writing here V1, V2, V3, V4 and V5 and V6. You see, if I write these vertices V1, V3 and V5 on one set, suppose. So now you can see V1, V3 and V5 we are putting on one set. Now V1, then definitely the other three will be in the other set. Now you see that V1 is connected with V2 and with V6. So V1 is connected with V2 and V1 is with V6. So that is the connection. Similarly, you can see V3 is connected with V2 and V3 is connected with V4. V3 is connected with V2 and V3 is connected with V4. Similarly, with V5, the V5 is connected with V4 and V5 is connected with V6. V5 is connected with V4 and V5 is connected with V6. So this is a bipartite graph. Here you can see that V1 is a different set and V2 is a different set. If you take the union, all the vertices will be there, but now you can see each vertex of this is connected with some vertex in the set V2. But none of the vertices have edge. For example, in this set V1, none of the two vertices are having an edge between those two. For example, V1 is not connected with V1, V3, not with V5. Similarly, in V2 also the situation is happening. So the condition of bipartite graph is satisfied. So we can define a bipartite graph like this. Now the complete bipartite graph. Now, for example, but before that, we have that K3 is not bipartite. You know, K3 is a complete graph of three vertices. This is K3 in fact, and you can write this is V1, V2 and V3. Of course, if you want to partition it in two sets V1 and V2, then you can see if you keep V1 here and V2 here and here, because V1 has connection with V2 and V3, so I can write like this and this. Now you know V2 has its connection with V1 as well as with V3, but V1 V2 has connection V1, it's okay, but once you connect V2 with V3, so that violates the definition of a bipartite graph. So therefore a K3 can never be a bipartite graph. Then comes the complete bipartite graph. Complete bipartite graph is what? A complete bipartite graph can be written as KMN. KMN. Mn corresponds to the partition. Suppose this is V1 and this is V2. Let it has m number of vertices. Number of vertices is m, and number of vertices here is n. So in this, that is why it is denoted by KMN. So a complete bipartite graph KMN is a graph that has its vertex set partitioned into two subsets of m and n vertices, like I have represented over here, respectively, with an edge between the two vertices. Edge between two vertices if and only if one vertex is the first subset and another vertex is in the second subset. In fact, in complete bipartite graph, if you understand in a simple language, is that each vertex of this V1 must be connected with each vertex of V2, and exactly in the same manner each vertex of this must be connected with each vertex in this set. That should be happening here. For example, this is K23. That means this is V1 consisting two vertices, and this is V2 consisting three vertices. V2. So now you can see each vertex here is connected with each vertex in V2. This is connected with this is connected with this is connected with this. Exactly here, each vertex is connected here with each vertex here. Exactly, if you look at the situation in other way, this vertex here is connected with all the vertices here, this one as well as with this one. Similarly, this is connected with this one and this one. This is connected with this one and this one. So similar situation is happening here. So this is in fact K33. So I can say that this is V1 and this is V2. You can see the same situation is happening here. Like this is a K35, this is K26, exactly in the same manner you can interpret the situation. So I think the concept of complete bipartite graph is clear to everyone. So that is it about this lecture. These are the reference books you can consult. Thank you about it.